Okay, so please sign this and to pass it around. I forgot my grade book, I think, at home. Okay, so let me start today's class. Now, as I recall, there was one more question in the collection of questions that that we looked at last time. Okay, so yes, so there was this question that we did not get, we didn't have time to get at. And in actual fact, this question here is in part reliant on the answer that we got here. So I need somebody to remind me of the answer that we got for the concentration of the free silver ion that, let me turn on my pen function here. Oh, you know what? Let me not do that. Let me see. Okay, so let me oh, I have it here. Cool. All right. So this is what we did from, thank you. This is what we did from last time. The last question that we did. So this answer is what we're going to need in order to move on to the next question. So 8.0 times 10 to the minus 10. So let me write that down here. The concentration of the silver ion that we calculated from the last time is 8.0 times 10 to the minus 10 M. All right. So we're going to need that in order to answer the last question. So the last question says, if 1.00 kilograms, I'm sorry, grams of potassium bromide are added to 1.00 liters of the solution described in the previous example, should any silver bromide precipitate from the solution? So what must be necessary in order for a precipitate to form from a solution where you have the possibility of two ions coming together to form a precipitate? There's one equation or one mathematical relationship that must be obeyed, or let me use obey, in order for precipitation to occur. And it is relation to whether or not it's the relationship between QSP and KSP. Anybody? In order for precipitation to occur, there must be an established relationship between QSP and KSP. What is that?
QSP is
No, actually it has to be greater. Right? QSP must be greater than KSP. I'm quite sure I've told you guys that if QSP is greater than KSP, our precipitate will form. If QSP is less than KSP, then no precipitate will be formed. And then if QSP is equal to KSP, basically the solution is saturated. All right. Or another way of saying is that there's going to be equilibrium between the solid state and the liquid state and the aqueous state, between ions and precipitate. Okay. So with that said, we already know what the concentration of silver ions are. Make this more presentable. Okay, so we already know what the concentration of silver ions are. We are given from this question that the amount of potassium bromide is 1.00 grams. So let me just put that here. Mass of KBr is equal to 1.00 grams. Volume of solution is 1 liter, and the KSP for AgBr for silver bromide is equal to 5.0 times 10 to the minus 13, 5.0 times 10 to the minus 13, right? So what the question is asking for is if, let me see the question again. The question is asking for, should any precipitate form from the solution, right? Okay, so what would you suggest we do in order to figure that out? We know what the concentration of the silver ions are. We know of the mass of the potassium bromide added. The volume of the solution is 1 liter. Let me recheck that here. 1.00 liters, I'm sorry. So let me correct that. 1.00 liters, right? That's the volume of the solution. And the KSP value is 5.0 times 10 to the minus 30. So my question to you is, how would you go about determining whether or not this much KBr in that much of a solution will form a precipitate? What is QSP equal to? Let me deal with that first. QSP, what's the equation for QSP? So concentration of silver ions times the concentration of Br minus, right? We already have this because that is this. So the question now becomes, how do we determine that? Right? Any ideas? Not quite. The hint lies in these two numbers right here. You're trying to find the concentration of bromide ions so that you can get the QSP value. So you're given the mass of potassium bromide as being 1.00 grams, and you're given that the volume of the solution is 1.00 liters. So how would you determine the concentration of the bromide ion? And you guys out there in Zoom can chime in as to what you think, or how do you think we should go about getting the concentration of the bromide ion? What would that be equal to? .00 grams of KBr. And then what do we do with that? Remember, we're trying to find the molar concentration of bromide, right? So far, we have the mass of potassium bromide. How would that help us to determine the molarity of the bromide? What kind of conversion would you do here? Okay, so the molar mass will go down here, the grams of KBr, and 1 mole will go here, right? So, you know me, I'm lazy. I'm going to use my trusty molar mass calculator to calculate the molar mass of KBr. Oh, wait a minute. Oh, wrong syntax. Uppercase B. All right. And according to this, the molar mass is 119.00. So we're going to put down here 119.00, right?
Oh God, middle school was.
Hello?
Never look.
Okay, somebody need to mute their mic. Okay. So this would give you, up to this point, would have determined the the number of moles of potassium bromide. What next? Remember, the aim is to get the molarity of the bromide ions. So you need to multiply this by another conversion factor. What would that be? What's the mole ratio between the potassium bromide and the bromide ions based on the formula? 1:1. So here we're going to put 1 mole of KBr down here and 1 mole of Br minus. So what we have determined so far is the number of moles of bromide. But remember, again, the question is, or not a question, but this part of the question, we are trying to find the molarity of the bromide ion. So now that we have the moles of bromide, then how would you determine the molarity? How would you determine the molarity given the moles of bromide? In other words, what would you divide this by? Because this is going to cancel with that, that's going to cancel with that. So up to this point, you have the moles of bromide. Exactly. You divide by the volume, which is 1.00 liters, right? So we need to do that calculation. So let me get my cheap calculator and do that calculation. So 1 divided by 119 divided by 1. So according to my calculation, this works out to be equal to, rounded off to 3 sig figs, 8.40 times 10 to the minus 3 M, right? So now that we have the concentration of the bromide ion, we can put that here, and we already have the concentration of the silver ions, which we can put here, right? So we're going to put 8.0 times 10 to the minus 10 multiplied by 8.40 times 10 to the minus 3. And that will give us a QSP. So let's see what that gives. 8 times 10 to the minus 10 multiplied by 8.40 times 10 to the minus 3. And according to my calculations, this gives you 6.7 times 10 to the minus 12. And then we have to compare it to the KSP. Where's the KSP? Here's the KSP right here, right? So when we compare 6.7 times 10 to the minus 12 to 5.0 times 10 to the minus 10, what do we notice? We notice that what? QSP is either what? Greater or less than? What is it? Greater. So QSP is greater than KSP, which means that a precipitate will form. And that's how that is done. All right. Any questions about this? Excuse me. Any questions? Any questions? Any questions out there in Zoom? Any questions out there in Zoom? If not, we're going to move on to the next chapter, which deals with thermodynamics. Okay, let me. Let me check something here. I know I published something this morning. I just don't remember. There's so many things. I keep forgetting what I've done or what I should do. Okay, so as far as assignments go, I've published, oh no, this is, let me see assignment 6. Okay, so assignment 6 is what we're going to work on now. Well, not right now, but after we cover a couple of things in the thermodynamics chapter. So basically, I've published everything up to assignment 5. All right. Okay, so let me get to the PowerPoint, which deals with thermodynamics. And these terms you see here, entropy, free energy, and equilibrium are all essential when it comes to this particular topic of thermodynamics. Okay, so first thing we're going to talk about is what we mean by this term spontaneous or spontaneity, all right? So basically, a spontaneous process is kind of different from everyday language in terms of how people tend to use the term spontaneous. In everyday language, people tend to use that term, to mean something very explosive or whatever, right? But in thermodynamics, when we're talking about this, whether or not a process is spontaneous, we're talking about whether or not that process will simply occur without any assistance on anybody's part, right? And here are several examples of that. Water runs downhill, right? That is a spontaneous process because we don't need to do anything in order to cause the water to run downhill. A lump of sugar dissolves in a cup of coffee. Again, that's another example of a spontaneous process. At 1 atmosphere, water freezes below 0 degrees and ice melts above 0 degrees. Both freezing and melting are spontaneous processes according to the conditions described here. Heat flows from a hotter object to a colder object. Again, that's another example of a spontaneous process. You will not see, or maybe I should say, it is highly unlikely that you'll see heat leaving a colder object and moving on to a hotter object, right? The second to last one, say a gas expands in an evacuated bulb. Again, that's another example of a spontaneous process. And iron exposed to oxygen to form rust. That's another example, right? In fact, any reaction that occurs without any assistance, those reactions will be spontaneous processes, right? So, as we said before, that's what spontaneous means. It means that a process can occur or will occur without any assistance on anybody's part, right? So the example that is shown here in the picture to the bottom right corner of the screen, you see somebody skiing down. That's a spontaneous process. You don't need to do anything in order to make that happen. But you see the person skiing up, that would be a non-spontaneous process. Some energy would have to be expended in order to make that person goes against gravity upwards the slope, all right? So in this case, it's an actual science, chemistry, physics example. Imagine you have two vessels connected by a tap right here. When you open this up, we all know what's going to happen if you have gas isolated in one of the two vessels right here. When you open this up, without anybody doing anything, the gas will simply expand throughout the whole apparatus, right? What is highly unlikely to occur is reverse, right? It's very unlikely that you see that you start off with a system looking like this, and then all of a sudden all the gas just simply move into one of the vessels, right? Something would have to be done in order to make that occur, right? So the first one is an example of a spontaneous process. The second one is an example of a non-spontaneous process, right? Okay, now in chemistry, the question was looked at, how can we predict whether or not a process is spontaneous? And one of the things that people were looking at before was the whole idea of enthalpy. Does enthalpy have any influence on whether or not a process is spontaneous, right? And if you do a cursory examination of different reactions and the corresponding enthalpy values, you'll notice that for reactions that are spontaneous, there are two common features. What you'll find is that the enthalpy is either negative, or if it is positive, the magnitude will be relatively small, right? And you can see that in these examples here. We have this reaction here, which is definitely spontaneous and is exothermic. The same is true for this one. Now, this one is not exothermic, but it is still spontaneous. And so is this one right here, right? Not exothermic, it's endothermic, but still spontaneous, right? But when you compare these last two, their values are relatively small in magnitude compared to the previous two. And if you look at most reactions, you see that to be the case. So what this seems to suggest is that enthalpy does play a role in terms of whether or not a process, or in this case, chemical reaction, will be spontaneous. But there must be something else that comes into play, so that we can make predictions as to whether or not a reaction will be spontaneous. So that leads us now to a second factor, which is known as entropy, right? What is entropy? Well, I mentioned this before, right? In order for a reaction to be spontaneous, the enthalpy is either negative or small and positive, right? So that's what that is saying. But I was saying here that entropy is another factor which comes into play in terms of determining whether or not a reaction is spontaneous. So what is entropy? So there is an actual technical definition for entropy, but we can work with this simplified version of the definition of entropy. It is a measure of the randomness or disorder of a system, right? So basically, the entropy of a system is how random or disordered it is. So the greater the order of the system, the lower will be the entropy. Or the greater the disorder of the system, the greater would be the entropy of the system, right? So greater disorder means greater entropy, because entropy is a measure of the degree of randomness or disorder in a system, right? And we can actually quantify entropy values. I'm going to talk about that later on, but we can calculate based on the values individuals of entropy of a system. We can calculate the change in entropy, which is the final entropy minus the initial entropy, all right? And basically, if you have a system, for example, where going from initial to final, there's an increase in randomness, that means that delta S is going to be positive, right? Because the final value would be greater than the initial value if the system becomes more disordered, right? And the opposite is true. If the system becomes less disordered in a particular process, then delta S is going to be negative, all right? Let me see what's next. Okay, so for a real example, if you have any substance that can exist in the three common states that we're familiar with, the solid, liquid, and gaseous state, then if you think about it, the solid state would be more ordered, right? And if you were to melt the solid, it becomes a liquid. And if you remember how liquid molecules behave compared to their behavior in the solid state, the liquid molecules will have a more random behavior in terms of movement and so on. So therefore, you can conclude that a liquid state would be more disordered compared to the solid state. So basically, the entropy of a liquid would be greater than the entropy of the solid of the same substance. And then, of course, as you go from the liquid state to the gaseous state is even more disordered. So therefore, the entropy of the gaseous state would be greater than that of the liquid and the solid state. So this is basically summarizing what I just described in terms of the order of entropy of the same substance in the three different states, right? So the entropy of the solid state will be less than the entropy of the liquid state, which in turn will be, it turns out, much less than the entropy of the gaseous state. And this is true right across the board for every substance without an exception, all right? So what's next? Okay, so here's the actual example. So if you're looking at the change from H2O solid to H2O liquid, would delta S in this particular case be positive or negative? You're going from the solid state to the liquid state. So delta S, the change in entropy, would you expect it to be positive or negative? Exactly, positive, right? Because you're going from a less ordered, or I should say a more ordered system to a more disordered system, all right? Okay, so delta S is positive. So this is just a summary of some examples of situations where the entropy change is positive, right? Going from a solid to the liquid, we talked about that already, right? That is, of course, an increase in entropy. Going from a liquid to the vapor state, same thing. And if you have a solid, or I should say a solute, dissolved in a solvent to form a solution, then also that would correspond to an increase in entropy. And even if you have within the same state, just a change in temperature, right? So let's say you have iron at, let's say, 50 degrees, and you heat it to iron at 80 degrees, right? Even though it's in the same state, there's an increase in entropy. Why? Because as you impart more energy to the substance, in the case of iron, even though it's in a solid state, the atoms themselves will vibrate around a certain equilibrium position. And with increasing temperature, there will be an increase in the amount of vibration. So therefore, as you increase the temperature for any substance, the entropy of that substance increases as well. Okay, so based on what we have just discussed, let's see if you can answer these questions. Or this question, it says, how does the entropy of a system change for each of the following processes, right? And the first one is the condensing of water vapor. So would that correspond to an increase or a decrease in entropy? I'm sorry? Condensing. You know what condensing means? Condensing means what? You're going from what state to what state? I'm sorry? From gas to liquid, exactly. So again, is delta S positive or negative? In this case, it will be negative. So there will be a decrease in entropy, and therefore delta S will be negative. Okay, how about this one? Forming sucrose crystals from a super saturated solution. So in other words, you're starting from a solution, and you're going to get some crystals out of it. Would that be a delta S positive situation or delta S negative situation? You're going from a solution, the ions or the molecules in solution, to the solid. So you're saying what? Exactly. So delta S will be negative. The entropy will decrease. Okay. Heating hydrogen gas from 60 degrees to 80 degrees. Is that delta S positive or delta S negative? Positive, exactly. Delta S positive because you're imparting, just like what I described earlier, you're imparting more energy to the system. The molecules will move around more randomly. And therefore, that corresponds to an increase in entropy. Okay, subliming dry ice. Does anybody know what the term sublime means? Or sublimation?
Oh, it's like from gas to solid.
No, the other way around. From solid to gas. Right, like dry ice. You're familiar with dry ice? Right. If I take a piece of dry ice and put it on a bench here, eventually it will decrease in size because the solid carbon dioxide, which is what dry ice is, will be converted to gaseous carbon dioxide, right? Okay, so would that sublimation process, would that be a positive or negative change in entropy? Positive. Delta S would be positive. Okay. And I think there should be one more. Oh, no, that's it. All right. So let me get you guys started on number 6, assignment number 6. And I want you to focus on just question number 1 for now. Not taking too much in terms of time. Here we go. Here we go. Here we go. And for those of you out there in Zoom, let me go ahead and publish that assignment now. So this would be assignment number 6, which is now available. So you guys out there can download it and get started on it. I just want you to focus on question number 1, which is not much. So I'll give you a couple of minutes and then we'll move on to discussing some other things about entropy. Did anybody come in late? Did you sign this? Okay. I forgot my grade book, so this is attendance. And pass it on to young man back there. Okay, are we finished? Finished? Okay, so let's continue our discussion of entropy. Now, entropy is yet another example of something that you would have met before in General Chemistry 1, and that is state function. And a state function are basically properties that are determined by the state of the system, regardless of how that condition was achieved, right? And you see listed here examples of state functions, which would include energy, enthalpy, pressure, volume, temperature, and what we just discussed, entropy, right? And this diagram here basically shows you the fact that if you have a substance in one state and it changes to another state, the change in the state function would be the same regardless of the pathway taken from the initial state to the final state. So they're using this as an analogy to demonstrate that. Now, in terms of entropy, these values, entropy values, can actually be quantified. And this table here is basically a small sample of different substances and their entropy values. Now, in Canvas, I've posted a more comprehensive list. Let me show you where that is listed. And of course, you'll have access to this particular table during your tests or exams. And that would be here, actually here, thermodynamic data. So if you click on that, and if you have had me before in General Chemistry 1, you'll see this already, but we didn't use all of it. It's the same table as back then. Okay, so this is the table I am talking about, right? So basically, you have 3 columns here for the different substances. For those of you who have had me before, we were focused on using this column right here, right? But for this course, you'll be using these 2. Now, what we just talked about is basically located in this column right here. This is the entropy column, all right? So if you want to look up the entropy values of anything, this is what you're going to look at, right? So that's the table that you'll have access to, and you can use that table to calculate the actual change in entropy, which I think the next slide, maybe not the next slide, but a future slide. But before we get to that, let me talk about the first law of thermodynamics, which you should have met before as well, which is the energy can be converted from one form to another, but energy cannot be created or destroyed. And I should add, this is only true for physical and chemical processes. The second law of thermodynamics has to do with the entropy of the universe. And it says that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. So we can express this mathematically. We can say that for a spontaneous process, the entropy of the universe, which is equal to the entropy of the system plus the entropy of the surroundings, will be always greater than 0, right? And I should add that this should be read as a change in entropy of the universe, right? So the change in entropy of the universe is going to be greater than 0 for a spontaneous process, and then for a non-spontaneous process, or I should say an equilibrium process, the change in entropy would be equal to 0, all right? So that's basically the mathematical representation of the second law of thermodynamics. So this brings us now to what we call the standard entropy of reaction, which is the entropy change for a reaction carried out under the conditions of 1 atmosphere pressure for gases and a temperature of 25 degrees Celsius, right? And if you were to calculate the change in entropy for a hypothetical reaction such as the one that you see here, you're going to see that the process is very similar to how you'd calculate the standard enthalpy of a reaction. If you remember how to do that from General Chemistry 1, it's the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants, right? It's the same idea. The only difference is that you'll be using entropy values, right? So in this hypothetical example right here, this reaction right here, the change in entropy of the reaction would be the sum of the entropy of the products. And of course, you have to multiply the respective entropy values by their coefficients according to the balanced equation, minus the sum of the entropy of the reactants. Again, you have to take into account the coefficients multiplying each of the entropy values. Okay, so that will give you the change in entropy. And of course, these values you'd have to obtain from the table that I would have provided for you, all right? So basically, to summarize, it's a sum of the entropy of the products minus the sum of the entropy of the reactants. So for example, let's say you're given this equation and you're asked to determine the entropy change for that reaction. So basically what you'd have to do is look up the entropy values for the different substances, which are given right here. And then you plug it into this equation. In fact, the next line I have here is the equation that you'd actually use based on this balanced equation. It would be 2 times the entropy of carbon dioxide, because you have the 2 here, right? Minus 2 times the entropy of the carbon monoxide plus the entropy of oxygen, and all of that would be in the parentheses. So this is for the products, this is for the reactants, and then all you have to do is plug the numbers in. 2 times the entropy of carbon dioxide gives you this number, and 2 times the entropy of carbon monoxide gives you this number, plus the entropy of oxygen, which gives you that number, and then you do your number crunching and you get your value. And please note, I should have made mention of this before, please note the units of entropy, right? It's joules/Kelvin per mole, or times mole, I should say, right? So that's the unit of entropy. Okay, any questions about this example? Any questions? Any questions? All right, let me see here. Okay, entropy changes in the system. Now, what we're looking at here are situations where you may not be asked to calculate the actual value, but basically tell whether or not the entropy change will be positive or negative, right? So, and this is specific for systems where gases are involved, right? So it says if a reaction produces more gas molecules than it consumes, then we can automatically assume that the change in entropy will be positive, right? So if you have more gas molecules on the product side compared to the reactant side, then the change in entropy would be positive. The reverse is true, of course. If you have less gas molecules on the product side compared to the reactant side, then the change in entropy would be negative. And if there's no net change, right? So I'm talking about a reaction like, for example, 2HI gas to give H2 gas plus I2 gas, right? So in this equation here, you have 2 moles of gases on either side, right? So there's no change in the number of molecules. In that situation, you cannot tell exactly if it's going to be positive or negative, right? However, you can predict safely that whether or not it's positive or negative, the magnitude is going to be very small, right? So that's the best you can do in terms of predicting, you know, the enthalpy change when it comes to reactions where you have equal numbers of molecules of gases on both sides, right? So based on what we have just discussed, let's see if we can answer this question. It says, what is the sign of the entropy change for the following reaction? And it gives you the equation right there. So will it be delta S positive or will it be delta S negative? Exactly, it's going to be delta S negative, right? Because you have 1 mole of gas on the left side, no gases on the right side, so therefore the delta S value will be negative, all right? And this is just talking about what happens to the surroundings if you have a certain change occurring in a system. So let's say we're talking about an exothermic process happening in this vessel right here, and heat is generated and basically emitted to the surroundings. The result of that is that the entropy of the surroundings, the rest of the universe, would increase. And here it's the opposite if we're talking about an endothermic process, in which case the entropy of the surroundings will decrease. And this is just basically, well, this is talking about the third law of thermodynamics, which says that the entropy of a perfect crystalline substance is 0 at absolute temperature, absolute 0 temperature. In other words, 0 Kelvin. So basically what we're talking about here is that if you're able to cool any substance down to 0 Kelvin, the particles or the molecules or the ions will simply remain, will have no energy, or I should say no kinetic energy, no vibrational, no rotational, no translational energy. And in other words, we're talking about a perfect crystal, all right? So that's basically what the third law of thermodynamics says. Okay, so going back to the assignment, based on what we have covered, so far. You should now be able to do questions number 2. Let me see here. 3. 4. Okay, so questions 2 through 4. All right. And please use the values from the table that I mentioned before. So the table I'm talking about is this table right here, right? And by the way, this table has about 8 pages, so it wouldn't make any sense for me to just leave this up here because I'd have to scroll down. So you can bring it up on your devices and use it to answer the questions. And I think I remember there was one that is not in this table. Which one was it? I think it's a carbon. Hold on, let me check something here. Okay, there's only a value for liquid carbon tetrachloride. I'm talking about question number 2D. So let me look up the value for the gaseous phase. So entropy of gaseous carbon tetrachloride. Let's see what that gives. Okay, so according to this right here, let me see if I can find some more reliable source like this. Okay, let's see here. Yes. Okay, so according to this, the entropy of gaseous carbon tetrachloride is 309.65 joules per mole Kelvin. All right, so make a note of that, folks, because this one is not in the table. All right, and I see somebody asking a question. Can you do 2A as an example? Oh, okay, so Ms. Jones is asking for me to do the first part of number 2. Okay, so let me well, I would have to look up the values as well in order to do this. So we're going from C graphite to C diamond. Okay, so I'll have to look up the values. So let me go here and okay, let me see here. Oh, here, I have it already. Okay, so here are the values right here. For diamond, it's 2.377, and for graphite, it's 5.740, right? So all I have to do is, remember now, it's always products minus reactants. In this case, we're dealing with change in entropy. So delta S standard will be equal to 2.377 joules per mole Kelvin minus for graphite, which is 5.740 joules per mole Kelvin, and whatever that gives, 2.377 minus 5.740. So according to my calculation, this works out to be equal to minus 3.363 joules per mole Kelvin. And that's it. That's how you do that one. Yeah, it's the same idea for all the others. It's always the products minus reactants. And remember, So this is a common error that students tend to make. Remember to multiply the respective entropy values by their coefficients, right? While you're doing that calculation. I'm sorry? Oh, that means standard. Excuse me. Whenever you see this here, that means that the measurements are under standard conditions. And when we say standard conditions, we're saying that the temperature is equal to 25 degrees Celsius. And if there are any gases involved, their pressures would be 1 atmosphere. All right, so those are the standard conditions. And you see that symbol not only for entropy, you see it for enthalpy, and you're going to see it later on for free energy, which we'll talk about next. Oh, and another thing I need to mention. So whenever you're doing these type of questions, pay close attention to the state symbols. You know, the solid, gas, liquid, and so on. Because what you'll find is that the entropy, and I'm quite sure you're aware of this by now, the entropy of a substance in a solid state will be different from the entropy of the same substance in a liquid state. So you have to, whenever you're doing these calculations, pay attention to the state symbols. Let me see, somebody said something here. Oh, you're welcome, Miss Jones. I'll be right back. Okay, so like, for example, well, number 3 is an example of that. Let me see here. Here are 3 carbon plus 4H2, yes, to give C3H8. So now, gas. So now I have to go to the table and look at these values. I should mention that in this document here, I think it's the last page or last 2 pages. Actually, yeah, last 2 pages. They have a special set-aside table for organic molecules. And more specifically, well, organic molecules, right? So propane, C3H8 is such a molecule. And C3H8, propane. And according to this, the entropy of that is 270.2. Joules per mole Kelvin. And in the case of graphite, which is carbon, which I think is back up here somewhere.
It's 5.7.
Yeah, you're probably right, but I like to verify that. Yes, you're right. 5.740. And for hydrogen, H2, 130.68 joules per mole Kelvin. So now we can get down to the actual math. So delta S standard would be equal to S standard for C3H8 minus the sum of S standard for carbon plus, multiplied by 3, by the way, plus 4 times standard S for hydrogen. And all we have to do from here is plug the numbers in. So for propane, it's 270.2 joules per mole Kelvin minus 3 times the entropy of carbon, which is 5.740 joules per mole Kelvin, plus 4 times the entropy of hydrogen, which is 130.68 joules per mole Kelvin. And we'll just do the number crunching. So 4 times 130.68 plus 3 times 5.740 equals that. And then I'm going to subtract that from 270.2. Okay, I did something wrong. Let me do this again. 4 times 130.68 plus 3 times 5.740. And then I'm going to add to that 270.2. Okay, so according to my calculation, this works out to be minus 269.7 joules per mole Kelvin. And let me just say that one of the things when you're doing problems like these, you know, I like to tell my students, don't just plug in numbers and just follow everything blindly. See if the answer makes sense. For example, in this particular case here, I'm more confident about this answer because of the fact that I have a negative answer. Because just looking at the equation right here, I can see that delta S would be negative, right? Because you have one gas molecule here, you have 4 here. So as you go from greater numbers of gas molecules to less, that means that the entropy decreases. So, it makes sense. All right. Okay, so we're finished with number 3. All right, so let's see what next. Okay, so now we're going to get into how we can actually predict whether or not a reaction is spontaneous. And this has to do with a particular state function known as the Gibbs free energy, symbolized by the letter G, and we can calculate the change in the free energy, which would be symbolized by delta G, right? Now, the actual definition of free energy is the energy associated with a chemical reaction that can be used to do work, all right? And in the case of a process where the temperature is constant, this is the relationship between the Gibbs free energy of a system, the enthalpy of the system, or the enthalpy change associated with the system, and the entropy change that's associated with the system. So this equation here is basically what we use to calculate delta G. And delta G itself gives information as to whether or not a particular reaction is spontaneous, right? So if delta G is less than 0 or negative, that means that the reaction is spontaneous in the forward direction. If delta G is positive, that means that the reaction is non-spontaneous in the forward direction. And in fact, it will be spontaneous in the reverse direction, all right? And then we have the final option where delta G is equal to 0. That basically means that the reaction is in equilibrium, all right? So delta G is what we look at in order to determine whether or not a reaction is spontaneous, right? And as you can clearly see from the equation, there's an enthalpy component, delta H, right here. And then there's the entropy component, which is represented by T delta S, right? So it's this combination which allows us to determine whether or not a reaction is spontaneous. And we can determine what is known as the standard free energy of a reaction. In fact, we have tables that produces that. Again, you see the small 0 there as a superscript. That means standard conditions. And basically, these are the standard conditions right here, all right? So if you have a reaction, again, the same hypothetical example that I showed you before, then basically it's the same idea in terms of calculating the delta G of a reaction. Now, the delta GF here that you see here, that stands for the free energy of formation, right? And it's kind of similar to the enthalpy of formation that you'd have met in General Chemistry 1. Basically, what this is saying is that this is the free energy of a reaction where you have 1 mole of the product being formed from its elements under standard conditions. And again, you can identify these values in the table that I showed you earlier. So that would be the middle column. Oops, sorry. That would be the middle column given here, right? That's delta G formation, right? And you'll notice that there are some similarities between delta G and delta F in that for elements in their conditions under normal conditions, the values of delta GF and delta HF are zeros, right? So for example, aluminum, which is an element, arsenic, which is another element, barium, which is another element, all elements have a value of 0 for their change, for their formation, I'm sorry, for the free energy of formation of those elements, all right? Okay, so I just thought I should mention that. So going back to the PowerPoint. Okay, so this is the definition of the free energy of formation I mentioned before. It is a free energy change that occurs when 1 mole of a compound is formed from its elements under standard conditions. And this is what I made mention of a while ago, that the free energy of formation of elements in a stable state or form is equal to 0, all right? Okay, so based on what we have just discussed, you should be able to do this question. What is the standard free energy change for the following reaction? And it gives you the equation right here. So what you'd have to do is, of course, remember that the free energy of the reaction is equal to the sum of the standard free energy of the products minus the sum of the standard free energy of the reactants, right? So we set up this equation here. Again, you multiply each of the free energy values by their respective coefficients. This would represent the state of affairs for the products. That would be for the reactants. Now, please note that there are two reactants here, but we have oxygen here, which is an element, right? So we can automatically assume that the free energy of oxygen is 0 in that case. And then we put the numbers in. Of course, these numbers will come directly from the table that I would have made available to you. And then you do your number crunching and you see here that the free energy of the reaction here is equal to minus 6,405 kilojoules, all right? So that's basically what happens. That's typically how you do this type of calculation. And if I'm not mistaken, based on what we have just done, you should be able to do question number 4. And, well, not quite 5. Well, you should be able to do 5, yeah, come to think of it. Okay, so 4 and 5 you should be able to do, but I'm going to leave you to try those on your own, all right? Okay, any questions about this example? Any questions? Yes, sir.
So any element that have no.
Exactly. All elements under normal, the standard conditions described, their free energy would be assumed to be 0, right? That's oxygen, hydrogen, silver, copper, whatever, right? Okay, any other questions? Any other questions? Okay, is this reaction spontaneous at 25 degrees? And the answer is this reaction spontaneous? Remember about spontaneous reactions and delta G. Let me go back to remind you, because apparently you guys have forgotten. Remember this? And by the way, Ms. Jones, you're absolutely right. The answer is yes. But remember this here, right? If delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is non-spontaneous, but spontaneous in the reverse direction, right? So since the answer is negative for the example that we just looked at, we can say that the reaction is spontaneous. All right? Okay, let's see what next. Okay, so let us look at this equation more closely, because what you're going to see is that the final outcome in terms of whether or not delta G is negative is dependent on the magnitude of delta H and the sign of delta H, the magnitude and sign of delta S, and the magnitude of the temperature, all right? So we're going to look at different situations here, starting off with a situation where delta H is positive and delta S is positive, right? So if delta H is positive and delta S is positive, the question is, will this reaction or any reaction that have that situation be spontaneous? And the answer is it depends. And what does it depend on? The temperature. It depends on how high or how low the temperature is. So as stated here, if the temperature is high, think about it now. Delta H is positive, delta S is positive, and temperature here is high, so high that this part here is greater than this part. So if T delta S is greater than delta H, what does that mean for delta H? I mean, what does that mean for delta G? If delta H and delta S is positive, but T is so high that T delta S is greater than delta H, then what does that mean for delta G? Right, because delta G is negative, exactly. So that's what's stated here. Reaction proceeds spontaneously at high temperatures, right? And then now, if the reverse is true, if T is so low that this part here is less than this part, then delta G would be positive, which means, exactly. So that's what they're saying here. At low temperatures, the reaction is spontaneous in the reverse direction, not in the direction originally, right? And an example of this would be this reaction right here. Okay, let's look at this second situation. What time is it, by the way? I'm losing track of. Oh, no. Having so much fun. Okay. I think this is going to be the last thing we're going to discuss. So in this particular case, delta H is positive and delta S is negative, right? So if delta H is positive, whoops, sorry. If delta H is positive and delta S is negative, in fact, let me write this down here. If delta H is positive and delta S is positive, what does that mean for delta G? Well, if you think about it, if delta H is positive and delta S is positive, the result will be that delta G is always going to be positive, right? You have a positive number. Well, actually, hold on, wait a minute. I'm sorry, I misspoke. I misspoke about delta S, my bad. Delta S is negative. So if delta S is negative, think about this. If delta S is negative and delta H is positive, this minus sign will make all of this positive. So we have positive plus positive, which means that delta G will be positive, which means that the reaction will be non-spontaneous. All right? Or you could say that in the reverse direction, the reaction will be spontaneous. And this will be true at all values of temperature. All right? So that's what happens if delta H is positive and delta S is negative. Now, if the reverse is true, if delta H is negative and delta S is positive, then what does that mean for delta G? And the answer would be that delta G would be negative, because if you think about it, if this is positive, minus T delta S would be make all of that negative. So if you put a minus sign in front of this, that would be negative. So we're adding a negative number to a negative number, which means that delta G is going to be negative, which means that the reaction is going to be spontaneous going in the forward direction and non-spontaneous in the reverse direction, all right? And then the final one here, let me erase all this here to avoid confusion. In the final one here, if you have delta H, which is negative, and delta S, which is also negative, the question is, what would be the sign of delta G? And the answer again is, it depends on the temperature, right? So let's look at what happens when the temperature is high. If the temperature is high, right, that means that, well, firstly, this negative sign here will make this part positive and this part negative. So if the temperature is high, that means that this would be of a higher value compared to this, which means that delta G would be positive, right? So basically, the reaction will not be spontaneous under high temperature conditions. On the other hand, if the temperature is low, right, then what would that mean? That means that delta H here would be of a higher magnitude, which is negative. This is positive. So in that case, delta G would be negative, which means that the reaction is spontaneous in the forward direction, all right? So that's basically how you can qualitatively interpret or predict whether or not a reaction is spontaneous based on the signs and magnitudes of the enthalpy part of the equation, which is delta S, and the entropy part of the equation, which would be the T delta S. All right? Okay, any questions about this? Any questions? Any questions? Okay, I think I'm going to stop here for today. Because I don't want to start this topic and then stop in the middle of it. So make sure you attempt questions, all the questions up to number 4. And I think what I'm going to do is, you can try number 5, but I'm going to, next class, I'm going to do at least one of these questions so that you have a good feel for that type of question, all right? But you can try it on your own if you so choose. All right, so that's it for today, folks. I'll see you guys on Wednesday. So take care.
You'll have my water bottle in your office.
I think so, yeah. All right, then let me get myself together and.
Yeah, I couldn't come Wednesday, unfortunately, but,
Hmm.
so you said your office hours are when?
Today, I don't have my grade book here, so I don't remember, but I think it's from. I have a class that ends at 2, so I think it's from 2 to 6 or something like that. It's in the syllabus, but I'm quite sure it's 2 to 6 today,
Okay.
if you can make it.
Probably not, but Wednesday for this class, could you just bring it in?
Oh, yeah, sure, no problem.
Okay, but I'll actually,
Mhm. Yes, ma'am.
This for the rest of the assignment. I only did the part that I said, what you want me to do, I don't know how to do the rest of the assignment.
Well, that's why you need to come and see me or contact me on Skype, and then I can help you through those problems.
Yes,
So if you can do them, make sure you send them in to me. If you need any help, feel free to call me. All right? Yes, ma'am.
messaged me this morning saying that I could